Hello everyone, my name is Yunus Rabi Isa, popularly known as Bodmas. Welcome to our new tutorial video on the continuation of solving thermodynamic problems from MIT. This is one of the challenge problems that you can never find its solution on internet. So we sacrifice our time to solve and deliver it to our young generation university student at all or at large. So here is a question. We are going to start with reading the question as usual. The question: an adiabatic cylinder, sketch below, contains nitrogen gas modeled as an ideal gas and a block of copper separated by an adiabatic membrane. Initially, state 1. The pressure and temperature of the gas are 6 exponential 5 Pascal and 27 Kelvin, 270 Kelvin respectively. The copper block temperature is 380 Kelvin. A heavier adiabatic frictionless piston, mass equal to 45 kg, is pinned at a height of 20 cm above the surface of the copper block. The copper block is 1 cm thick. The surface area of the piston is 50 cm square. The density of copper is H.96 gram per centimeter. The specific heat capacity of copper is 385 joule per kilogram per Kelvin. The gas constant for nitrogen is 297 joule per kilogram per Kelvin, and its specific heat capacity at constant volume is 741 joule per kilogram per Kelvin. Please assume ambient pressure is 0, absolute, outside of the cylinder. A. What is the mass of contained nitrogen gas? B. What is the mass of the copper? The pin is removed and the piston settled to a new position, state 2. What is the position of the piston in state 2? What are the temperature and volume of nitrogen gas in state 2? What is the entropy change of the gas, piston, and copper during the transition from state 1 to state 2? The thin adiabatic membrane is now removed with no work or heat transfer with the environment. After some time, the system settles state 3. F. What is the temperature of the system in state 3? What is the position of the piston in state 3? What is the total entropy generated in transition from state 2 to state 3? What is the sign of entropy change for the copper block as shown in the diagram below? So this is a representative diagram. As you can see, this is the thickness of the copper, 1 centimeter. This is the height of nitrogen gas. It's inside a block, which is an adiabatic membrane by a piston. This is a piston and this is a pin used to pin the piston, to hinge the piston. So this piston is the one which is responsible to block nitrogen from going off. So that is it. So the copper is in adiabatic membrane. So that is a representative diagram of the question. So we start with solution. Solution. So A, we asked to find the mass of nitrogen content. So we use an equation of state, that is Pb is equal to mRT. So now M is equal to, that's the mass of gas, is equal to Pb over RT. So we can use either state 1 or 2 depending on the value we have. The mass of gas is either be equal to P1 B1 over RT1, or we can use state 2 P2 B2 over RT2. So we don't have state 2, so we can use state 1 to get the mass of gas. So mass of gas is equal to P1, that is 6 exponential 5, as we have given from the question, times the volume. The volume is equal to the area times the height. So the area is 50 centimeter, we convert it to centimeter square, we convert it to meter, times the power of -4, times the volume, which is 20 centimeter, we convert it to meter, then -2. All over the gas constant, which is 297, times the temperature 2 T1, which is 270. So this is equal to 7.4 H2 exponential -3 kilogram. So that is the mass of nitrogen content. Then B, we asked to find the mass of the copper. So we have given the density of copper. Even if we happen to be given, we know the density of copper is fixed. So from density is equal to mass over volume. This implies that mass is equal to density times volume. Therefore, mass of copper is equal to density of copper times the volume of copper. So what is the density of copper? Is H.96 times the volume, that is this is gram per centimeter, in gram per centimeter cube, times the volume of copper. So the thickness of copper will be the height of the copper, which is 1 centimeter. So the volume of copper will be the area times the height. So the area is 50 times 1, that is in centimeter cube. We don't have to convert here, this centimeter will go with centimeter. So the mass of copper is equal to 4H gram, which is equal to 0.44H kilogram. So that is the mass of copper. Now C. Now the pin is removed. So the pin is removed. So now we apply first law of thermodynamics. So now what is the system? So our system, we take gas and the piston to be our system. So the gas and the piston as our system. So now what is the interaction? Interaction. So our interaction, there will be no heat transfer since gas and piston are our system, and the copper is poured in an adiabatic membrane, so there will be no heat transfer to the copper. Copper is inside adiabatic membrane, so no heat transfer, and also no work transfer, no heat, no work. So what are our states? So state 1, before pin is removed at the initial state, and then state 2, the final state, after the pin is removed. So after the pin is removed, at the equilibrium state. So now we apply the First law. So by First law, heat minus work transfer is equal to the change in energy of the system. The change in energy of the system. So heat is 0, work is 0. This implies that the energy of the system is 0. What are the system? The gas plus the piston. That's our system. So it's equal to 0. So this implies that mass of gas, specific heat capacity of gas during change in volume into the temperature 2 of gas, at the final temperature state 2, minus initial temperature of the gas plus the mass of piston into the change in height, that is H2 minus H1, is equal to 0. Gas, it has internal energy. Has internal energy. That's the internal energy. No potential and kinetic energy. Well, piston has no internal energy, has no kinetic energy. It has only potential energy. Let me do it here. The change in energy of gas is equal to the change in potential energy of the gas plus the change in kinetic energy, change in kinetic energy of the gas plus the change in internal energy of the gas. So no potential energy, no kinetic energy, we have only internal energy, which is equal to the mass of gas Cb into T2 minus T1. So that is what I get here. And then that of piston, change in energy of the piston is equal to the change in potential energy of the piston plus the change in kinetic energy of the piston plus the change in internal energy of the piston. So no kinetic energy, no internal energy, we only have potential energy. So the change in potential energy will be what? That is mg. So there is g here, sorry, there is g here. So we have mp, that is the mass of piston, g, change in height, that's why we put change. So we have h2 minus h1. So that is it. So therefore, so we can call this to be equation 1. Let me derive equation 1. So that is mass of gas, specific heat capacity of the gas during change in volume, theta 2 of the gas minus theta 1 of the gas, plus the mass of piston into H2 minus H1 is equal to 0. To let's call this equation 1. Let me call it equation 1. Now to get equation 2, what are unknown here? The unknown here is H2 and theta 2. We have everything, but we don't have the H2, that is the final state. H2 and theta 2. So to get H2 and theta 2, we need another equation. We cannot solve one equation and get two unknown. So we need another equation. So to get another equation, we consider the force balance. The force balance. The force balance of the piston. The gas is trying to move the piston up. The piston is trying to move the gas down. So there must be a force balance for which the process is maintain equilibrium. Let me have a representative sketch for better understanding. So assuming this, so we may have, if this is a piston, so from the center of the piston we have what? The weight, mg. So the gas is trying to what? To act off. So it's trying to get out. So this is what? Force times area. That is, pressure. So that is pressure. From force is equal to pressure times area. So this is what? The force. This is the force. So that is the force balance. And now there will be an atmospheric pressure here times the area, but atmospheric pressure is assumed to be 0 from the condition given. So we don't have the effect of atmospheric pressure. So this is a piston. So now by applying the Newton's law of motion under equilibrium, summation of f of y equal to 0 along y-axis, and summation of fx equal to 0, summation of moment equal to 0. That's the equilibrium condition. So but we only have our force along y-axis, so you consider y-axis. So now taking off as positive, if we take off as positive, what will happen? So P2A minus mg minus is equal to 0. So this is 0 from the question. Atmospheric pressure is assumed to be 0. That's the ambient pressure. So this means that P2A is equal to mg. That's the mass of the piston. So now what is P2? So P2 is equal to mass of the piston times acceleration due to gravity over area. So by substitution, what is the mass of the piston from the question is 45 times gravity, acceleration due to gravity, which is 9.81 all over the area, that is 50 exponential minus 3, which is equal to h.h exponential 4 Pascal, 1 Newton per meter square. So now we get the final pressure. So from equation of state, P2V2 is equal to mass of gas RT2 of gas. So now we make the temperature to be the subject of the formula. So T2 of gas is equal to P2B2 all over the mass of gas, then R. So we call this to be equation 2. We have B2, we have P2. This B2 can be substituted as, let me cancel this as equation. Yes, let me leave it as equation 2 because my unknown is T2 and H2. So this volume B2 is equal to the area times H2. So I substitute just. So is equal to P2 then times the area H2 all over mgr. So let me call this as my equation 2. Note this. So this is my equation 2. So we can solve equation 1 and 2 simultaneously. So we solve equation 1 and 2 simultaneously. So we solve them simultaneously. So we put equation 1 in 2. What will happen? So put 1 in 2. Put 2 in 1. So whenever we see T2, we substitute it by equation 2. So now from 1, so we have mg Cp of the gas into what is T2 from the equation 2, that is P2 H2 then times the area all over the mass of the gas times the gas constant minus T1 then plus mass of the piston into H2 minus H1 is equal to 0. Therefore, H2 times P2 times area Cb all over R minus mg Cb T1 of gas plus MP H2 minus MPH1 equal to 0. So by making H to be the subject of the formula, we get that H2 is equal to mass of the gas Cb theta1 of gas plus GH1 all over M G into 1 plus CB over R. So by substituting the value, we get H2 is equal to 1.0 to H. So H is 1.0 to H. Now consider H1 and H2. So H2 is greater than H1. So the piston is moving off. D from equation 2. Theta 2 is equal to P2 is equal to P2H2 times the area over the mass of gas R which is equal to H.H times 10 raised to the power of 4 times 1.02H times 50 exponential minus 4 all over 7.4H 2 exponential minus 3 times 297, which is equal to 203.5 Kelvin. So that is the temperature. So we can get B2 now. So B2 is AH2, which is equal to 50 exponential minus 4 times H2, that is 1.0 to H, which is equal to 5.14 exponential minus 3 meter cube. So now Roman E, we asked to find the entropy change. So the entropy change is equal to the entropy transfer plus the entropy generated. So the entropy change of the system, or you can get the entropy generated, which is equal to total entropy. We can say the entropy generated is equal to the entropy of the gas plus the change in entropy of the piston plus the change in entropy of the copper. So now we expect entropy generated to be greater than 0 if the process is reversible. So the change in entropy of copper is equal to 0. Why? There will be no interaction with the copper. There is no interaction with copper since it kept in what? Adiabatic membrane. So entropy generated of copper is 0. So here is 0. So what of piston? The entropy generated of piston is also 0. It's also 0. It's mechanically adiabatic actually. So therefore the piston entropy change of piston is 0. So entropy change is 0. So now the entropy generated is equal to the change in entropy of the gas. So now we apply the constitutive relationship. The change in entropy of the gas is equal to the mass of the gas, specific capacity during change in volume of the gas, into the natural logarithm of θ2 of the gas over θ1 of the gas plus mass of the gas R ln P2 over P1. So now by substitution we get the entropy to be equal to 2.086 joule per Kelvin. So therefore the S gen is equal to the change in entropy of gas, which is plus 2.086, which is greater than 0. So the process is irreversible and is possible. So F. Now they ask us to find the state, that is state 3. We settled another state. So now we applied some procedure we apply in stage 2. So now what is our system? Let's take the system. So what is the system? So our system, we take copper plus gas plus piston as our system from state 2 to state 3. So it's from state 2 to state 3. That is the question. From state 2 to state 3. So now what is the interaction? So the interaction no heat, no work transfer. So the state, so now our initial state will be state 2. Initial state is state 2 and the final state is state 3. So now we apply the first law of thermodynamics. So the first law of thermodynamics, the energy of the system is equal to the heat minus the work. So this is equal to 0 and this is 0, which is equal to 0. So this implies that the change in energy of piston plus the change in energy of the gas plus the change in energy of the copper is equal to 0. So what is the energy of the piston? So we have mass of the, now from state 3 to state 2. So now the mass is going to be the mass of the this is piston, so this is the mass of piston into H2 minus H3 minus H2, as we did in the previous one I solved. No internal energy in the piston, no kinetic energy, we only have potential energy. That's why we have this term. Yes. So now what of for gas? We don't have kinetic and potential energy of gas. We only have internal energy. So we have mass of the gas, specific capacity of the gas, into temperature 3 of the gas minus the temperature 2 of the gas plus the mass of copper, specific heat capacity of copper, into theta 3 of copper. This theta 3 is the same, we just leave it as theta 3 to avoid confusion, because it's equilibrium temperature. So we leave it as theta 3 because the theta 3 of copper and theta 3 of gas is the same. So let me call it theta 3, that's the temperature of state 3. So therefore minus the temperature 2 of the copper. That is theta 3 is equal to theta 3 of the gas is equal to theta 3 of copper. So let me call this equation 1. So this is my equation 1. So I have about 2 unknown. So I need another equation to get the unknown as I did in the previous one. So at state 3, P3B3 is equal to MRT3. So this is the same as B3AH3 is equal to MRT3. So what is H3? H3 is MRT3 all over P3A. So now at equilibrium, P2 of the gas must be equal to the P3 of the gas at equilibrium, which is the mass of the piston over time acceleration due to gravity all over A by applying Newton's law of motion. So comprising those terms, we get H3 is mass of the piston times gravity, mass of the gas R3 all over the mass of piston times gravity. The area go with the area from the above. That is I substitute P3 here. This is P3A. So this P3A is the same as mass of the piston times gravity. So the area go with the area. Let me do it here. So I have H3 to be equal to mass of the gas R3 all over P3A. But P3 is the same as mass of piston times gravity, acceleration to gravity over the area. So this is the same as mgr3 all over mpg over area times area. So area go with the area. So that's what I get here. So H3 is Mgr3 all over Mpg. So this is equation 2. So now we solve equation 1 and 2 simultaneously. We put equation 2 in 1. So we put equation 2 in 1. What will happen? So we have mass of gas times R into T3 minus T2 of the gas plus mass of gas Cb into theta 3 minus theta 2 of gas plus mass of copper, specific quantity of copper, into theta 3 minus theta 2 of copper, and is equal to 0. So making T3 subject as a formula, we get M R into Mg plus the R plus C close bracket T2G plus mass of copper, specific gravity of copper, theta 2 of copper, all over the mass into R plus Cb plus mass of copper, specific gravity of copper. So by substitution we get the temperature 3 to be equal to 372.42 Kelvin. So that is the temperature 2. So now G, piston, that is position 3. So from equation 2, H3 is Mgrt3 all over the mass of piston times gravity. So by substitution we get 1.876 meter. So B3 is AH3, which is equal to 9.378 exponential minus 3 meter cube. So H change in entropy of the system is equal to the entropy generated, since no heat transfer. So the S of piston plus the S of gas plus the S of copper is equal to entropy generated. So what is the entropy of the gas? By constitutive relationship, we have mass of gas, specific gravity during change in volume of the gas, ln theta 3 all over theta 2 of gas plus mr ln v2 over v1. So by substitution we get 4.67 joule per Kelvin. Joule per Kelvin. Then the entropy change of copper. The entropy change of copper. Copper is a solid, so the entropy change of copper is equal to the mass of copper, specific gravity of copper, ln T3 all over the theta 2. By substitution we get minus 3.747 joule per Kelvin. So the change in entropy of piston is equal to 0. Gravitational piston is mechanically isolated. So therefore the total change in entropy is equal to 4.67 plus minus 3.747, which is equal to 1.20. 1.20 joule per Kelvin. So that is the entropy. So entropy change is equal to the entropy generated, which is 1.20, which is greater than 0. The process is reversible and is possible. So that is the end of these problems. Thank you very much for watching us. Please subscribe to our YouTube channel. Bear with me in our next video. I remain my humble self, Inus Rabi Isa, popularly known as Bodimas. Thank you very much for listening.